Okay, so we looked at how torque fits together into Newton's laws. We got Newton's laws for rotation. The sum of the torques around some axis, any chosen axis, adds to zero if it's in rotational equilibrium. Now it could be dynamic equilibrium, rotating at a constant rate, or it could be static equilibrium, not rotating. Or the sum of the torques around that axis on some object, some circular object, some rod, is equal to the rotational inertia of that object around that axis times the angular acceleration of that object around that axis or origin. So it's just like net force causes ma, causes the acceleration. That mass resists it, here rotational inertia resists it. So that's how it goes in. You're familiar with that, that's nice. The tricky thing now is with rotations, we have to deal with the fact that objects have size. They've got some extension to them. And now we have to worry about that, and that's why we waited to learn about this until now. So what we need to do to get the net torque is look at the torque from each individual force. And that'll develop our awareness too. So calculating the torque from one force is the topic right now. And we want it to be around a chosen axis or origin. So you get to choose which axis or origin. Now if you've got a certain axis of rotation, then that's likely to be your axis or axle of rotation that you'll use for your mathematical analysis. Center of mass might be there. But you'll see other reasons for other choices later. But it's around some point. There are 4 ways to do this. You might say, can't you just teach me one and then I would just use that one? The problem with that is you won't develop an intuition. The first way that I listed here is the one we'll do last, and not right now. That is more general. That allows for rotations in any direction, and it uses the right-hand rule direction that you find in the vector or cross product, multiplying vectors. So see that video on multiplying vectors and make sure you can do the mathematics of multiplying vectors with the vector or cross product, where you end up with a vector. And so this definition is the torque from a force around some point or axis is, by definition, the R, which we'll define in a moment, cross F. That force that we're looking, the torque from that F is this much, okay? So that's one way we can do that. Again, more general, a useful definition when you need it, but you don't always need it. If you're drawing on the board, and if I move my finger like this, then we can all agree that's counterclockwise. If I go this way, we can all agree that's clockwise. You can choose either one to be positive. A lot of books call counterclockwise positive, partly because of the mathematical tendency to want to say that an angle is positive rotating up into that first quadrant. But we needn't do it that. Yeah, we can have counterclockwise be positive too. Of course, there's counterclockwise. And so for me, it's still counterclockwise. And yet for you now, it's clockwise. And so to deal with the fact that if I've got two sides that I'm looking on, I'll say it's counterclockwise, you'll say it's clockwise, we need to go here. But don't use this unless you have to. Okay, so this is a little more powerful, a little more general, but also a little more complicated. So we're going to look at torque using counterclockwise and clockwise. Choose one plus, the other one's minus. Okay. All right. So realize also, when I talk about this, that, kind of a tricky thing, if I'm going counterclockwise, that's counterclockwise, that's counterclockwise around that point, that's counterclockwise, and that's counterclockwise. Okay. So it depends on which side of the point you're on. Up over here can be counterclockwise, down over here can be counterclockwise. So when I'm adding forces, I look at vertical and horizontal usually, or x and y. But when I'm adding torques, I'm saying the sense of the rotation around. Left can be counterclockwise, right can be counterclockwise. Conversely, of course, this could be clockwise, So when we're looking at torques, look at the way in which it goes around. If these are different forces, say this is F1 and this is F2, they both torque, or twist if you will, counterclockwise, and so they would both have the same sign, say positive. Okay? And this would also have a positive F3 and F4. All these would be in the same direction for torque. However, if my problem requires that I add up forces as well, well then obviously F1 and F2 are opposite in the vertical direction, say, and these are opposite in the horizontal direction, say I'm using vertical and horizontal. So it's a different game. When you do forces, you got to look at your X, Y coordinate choice. When you do torque, you got to do the sense of going around a particular point. And that's confusing at first, but then it's not really too much of a problem, hopefully. Okay, so how do we calculate the torque from any individual force when using this counterclockwise, clockwise, plus minus method? So the torque from any force vector around any point that we've chosen is equal to, and I'm going to define these terms next, okay? So just write this down in your notes. It's either plus or minus, depending on which way, the magnitude of R times the magnitude of F, meters, newtons, times the sine of the angle. Now, whenever you see something like this, generally that angle is between those two, in particular between the lines of those two, which I'll discuss. So that you can have an inclined plane or all kinds of things, but that just cares about these two vectors, which we'll get to in a second. Or you can calculate it as plus or minus R perpendicular times F. Or you can calculate it and see it and have an intuition thinking about plus or minus R times F perpendicular. Okay. And you can kind of get a sense that the R perpendicular is going to be R sine theta. And the F perpendicular is going to be F sine theta. But the awareness is going to deepen as your awareness will deepen as you study this. Also, you'll find that in some problems, there will be dimensions that will be given, and this or this might be really easy to see. One of them might be easier than the other to see. Okay, this will always work, and it's not that hard to see, but push yourself to train and see and gain an awareness of these two things. It'll really it'll make you understand torque better. So let's go over here and talk about the definitions. So write this down, have it as your little cheat sheet, your little guide, right? And then as you do problems, follow it. And just like anything, when you're reading an instruction manual, they use words and what does that word mean? And you have to figure it out. So force is just a force like before. Force of gravity, force of contact, force of friction, force from a string. Often we have strings or rope tension pulling on rods and things like that. So any force that like before. But now we're dealing with extended objects. And so the point of application, that is where the force is applied, matters. And so you have to know this term, the point of application of the force, where it is applied on the object. Okay? And the line of force, which is really called the line of action, so remember it's called really the line of action, but it's the line of the force vector, so I could even put a little vector up there, the line of the force vector, is something we're going to use here in just a second. So how do you get it? Well, you see it by extending the force vector, so draw the force at the point of application, the force vector, and go forward and backward with a dashed line. Right? So if I've got a force here, F, then my line of force would just extend forward and backward, and I'll use that as a way, again, calculating correctly and deepening my intuition. So F, any force at some particular place that matters, then there's the line of F, and we'll be good to go. Now there's R. Okay. Oh, actually I pause. the force of gravity, mg. Of course, that acts on every single piece of an extended object. For most of our purposes, we can treat the force of gravity not on every piece, but at the center of mass and vertically down. So no matter how I tilt this, the force of gravity is down at its center of mass. R is from the tail, so this is, details matter, as engineers and scientists. So, excuse me, from, meaning the tail of R, the axis of rotation, to, that's where you put the tip of R, the point of application of the force. Do it a bunch, follow very slowly, and make sure you see that, and you'll get it, you'll learn it fast. And then you'll be off to the races. Of course, the line of R, we just use a dashed line and extend the R vector forward and back. Okay? So, R, from the axis of rotation to the point of application. Okay. Let's take a look here at some examples. If I have, let's do this. A rod here. If I choose my axis for some reason there, and I apply a force, maybe there's a string pulling up here, the tension force, then my line of F would be here. My R would be from A to F. As a vector. We can still use that vector cross product now. That's R. My line of R would be here. Okay? R goes from the axis or origin to the point of application of F. Line of R and the line of F. So let's see how that allows us to use these three different ways, really four different ways, of calculating the torque from that particular force. Let's go over here. And now let's define three more things, and you've got all the ingredients, and all you need is practice. So first, the angle. We said torque is equal to RF sine phi, plus or minus, right? So in that definition, we had the torque from some force around some axis is either in a positive sense or a negative sense. RF sine of the angle between them. Well, what do I mean, really, the sine of the angle between them? Well, this angle phi is either angle between the line of F, the line of action as it's usually called, and the line of R. So we just draw those lines, and why either angle? There's going to be a small angle and a big angle. Well, because the sine of phi is equal to the sine of 180 minus phi. Make sure you verify that. How can you verify it? Put in numbers. Put in 0 and 0. Put in 90 degrees. Put in 0, put in 180 degrees. Put it, check it out. Put in 30 degrees. And make sure you see that. So either angle works. Doesn't matter which one you use. Right? And what does that mean? If I've got R here, and my line of R here, and if I've got F here, and my line of F here, then I can use either one. I can use this as my phi, or I can use this 180 degrees minus phi. Either angle will still give me the same value. Okay, so that's fine. Okay, now, if I'm using the other definition, let's see, torque from F around some point A is positive or negative R perpendicular times F. What's R perpendicular? Again, it was not going to sink in entirely. You have to come back and review as you do problems. R perpendicular is called the lever arm. This is used a lot for engineers. The lever arm. It's what gives the leverage, right? The leverage. It's the shortest distance, or the perpendicular distance, from the axis of, or origin to the line of F. It's the shortest distance, right? From the axis of rotation. So go, in learning this, go slow to go fast. You go slowly, go from the axis. Okay, where's the axis? And then I'm going to go to the line. Where's the line of F? And let me go there. So let's try it out. Let's try it. Draw a little better picture here. And so my same old example. Let's go here. Here's my thing. There's my object. Here's my A. Maybe I've got a force here. Maybe it's a rope is attached, so the rope really extends up to there somewhere. And there's my line of F. And then I've got R, which is, let's see, R. R is from the origin to the point of application of F. And there's my line of R. And so I can see the angle phi. Sometimes that angle is called alpha, sometimes called theta, well, it doesn't matter. But what's R perpendicular in this case? What's the lever arm? How much leverage do I have? It's the shortest distance from the axis of rotation, so let me make sure that I follow these directions. From here to the line of force. That's not the shortest. If you're running a race and you start here, you don't run that way. You run this way.